All right, let's get started. Today, so one of the things we need to discuss is you have with regards to orbit determination. Given R and V in ECI frame or geocentric equatorial frame, you know how to find A, E, cap omega, I, small omega, and theta. Okay. So now one of your problems for the assignment is given these, you need to find R and B. How do you go about doing that?
Oh, the last one.
So this you know how to do. Now, given find R and B in the ECI frame. Okay. Now for that you need to understand a little bit about, we have actually discussed this indirectly, or we have discussed this in the context of coordinate transformation. Okay. If you apply the coordinate transformation, you know what geocentric equatorial frame is. How do you define the geocentric equatorial frame or the ECI frame? Right, geocentric is the origin is at the center of the earth. The x-axis is the vernal equinox or Aries direction. The z-axis is the axis of rotation. And y just completes the right-handed system. We have looked at that, right? Many times we have looked at geos. Huh? Y just completes the right-handed system. Y is z cross x. Okay. We've looked at that several times. The ECI frame is that. What does ECI stand for? Earth-centered inertia. This frame does not rotate along with Earth, it just goes around the orbit, but it does not rotate. It's fixed, it's not fixed to Earth. There is another frame called the ECF frame, Earth-centered fixed. So this rotates along with Earth. So every 24 hours, the ECI frame and the ECF frame align.
Every 1 hour?
Every 24 hours? Little more than 24 hours. Make sense? Doesn't make sense?
Yeah.
A little more than 24 hours.
Like 24.5.
Right.
That's why I have Is that why I have
That's not leap year. It's so what happens is, although this DCI frame is not, it's not rotating. When it revolves around, if it goes around the year for 365 days, it will complete how many degrees of rotation? It will complete 360 degrees of rotation. So every 24 hours, how many degrees will it complete? 1 degree.
1 degree.
Right? Approximately 1 degree. 365 degrees. 360 degrees divided by 365 days. So every this thing it will slightly moves. You understand? When it goes around Sun, this orbit, it will complete 360 degrees, right?
Yes.
So if it is if you think about it, think about this as Earth's orbit, okay? And this is Sun. So this would be that ECI frame. See, Earth is rotating while it's revolving around Sun. Right? This is Sun. And here you have Earth. This frame, this is the rotational axis of rotation. And this is that vernal equinox, the Aries direction. Okay, and it will be the same for this Aries constellation is so far away from this orbit. It doesn't matter where this is, where Earth is in the orbit. This Aries direction you can think about as it's pretty much there all the time. Okay? So when this, although this does not rotate, the Earth fixed frame, ECF, Earth centered fixed frame, will rotate as well as revolve around this frame. But this frame does not rotate, it just revolves. Even when it is revolving, what does it do? It actually completes that one rotation, 360 degree rotation. What is the time duration of this? Huh? 1 year, right? 365 point something, 0.25. So 360, that's the reason you have a degree you will make. So what you should understand here is, what are these three? What angles are they? These angles are the relative orientation of the orbit frame with respect to the ECI frame. These angles, cap omega, I and small omega, define the relative orientation. What does that mean? Cap omega is what? Right extension of ascending node. I is what?
Inclination.
Inclination. Small omega is what?
Somehow argument.
Argument of periapsis. So
So did you cover REC and DEC, the RA and DEC designation?
Yeah.
Yeah, but it was different ways. If you look back to like most of the like the orientation for this called transformation. That's it. He didn't call it DC. That's it.
Usually do like in class, take notes.
I know that actually what you just did.
And then when you're doing work, you brought them down, you can say about some of them, not what you did.
Yeah. So we did that.
Alright, let's take a look at this. Visible? So you see the XYZ frame over there?
Not all this.
That is the ECI frame. Okay? And these are your potential orbits. Okay?
So nothing can orbit over the Arctic Circle or North Pole?
There are polar orbits, yes. We looked at this, right? You remember this? Now, can you identify the two frames we're talking about, or the first frame we're talking about?
What does the PQW stand for again?
It's called perifocal frame.
Okay.
I see Z, Y, X.
XYZ is this. Okay? You have X, Y, and Z. You see it?
Mm-hmm.
That is the ECI frame, or the geocentric equatorial frame. Right? Geocentric equatorial frame. What is the plane in which this frame is defined? It's the equatorial plane. If you see this XY, the plane made by XY axis is the equator. Two lines will always form a plane. Okay? Two vectors will always form a plane. So what you're seeing here is X and Y form the equatorial plane. And Z is just perpendicular to that plane. If you know one, you can also define a frame by defining one plane and a direction in that plane. If you define one plane and a direction in that plane, you can also define a frame like that. So if this is my plane, and let's say one of my directions is starting here. One of my direction is this, going down. So this is one of the directions. Since this is the plane, this is the other direction by default. And if I take the cross of these two, I'm going to get this as the other direction. Okay? Make sense? Now, you have to define a frame, a coordinate frame in the orbit as well. You see it? There are two planes here. There is equatorial plane and there is orbital plane, right? You define two frames in two planes. Two planes equatorial plane and orbit or ecliptic plane. And the corresponding frames, two coordinate frames. So you define x, y, z direction to define that coordinate frame. X, y, z for equatorial plane. Okay. This is the ECI. This is what we call the ECI frame. And then the other one is PQW for orbit or ecliptic. Okay. So this is simply the PQW frame or perifocal frame. Now PQW, how do you define PQW? It is again very simple. You define the P direction. What is the plane for this? What is the plane for this? Yes, look here. Two planes, two frames. Correlate. Equatorial plane, ECI frame. Orbital plane, PQW frame. Can you correlate? Okay. You just need, so what is the x direction? X direction is defined in the equatorial plane. X direction. Equatorial frame. Z direction is perpendicular to equatorial frame. Y is simply Z crossed with X.
That's the Aries right after X direction.
Right, that is the Aries.
Yes, defined as what?
Huh?
X direction.
Defined
Oh,
in equatorial frame. Equatorial plane, sorry. Yeah, this is these three together will form what? DCI or geocentric equilibrium. Now, how about PQW? What is P direction? P direction is the periaxis direction. Periaxis or peri. Always.
What happened with the y equals z cross x? What was the explanation behind that?
It completes. So if you take y, if you know x direction, z direction, y will be z cross x. You need three orthonormal directions, orthonormal bases. This defines the orthonormal basis. How many axes do you need to define a coordinate system? Three. So these are three axes. X-axis is Aries direction, Z-axis is axis of rotation, Y is Z cross X. So wherever your X and Z are, if you define X and this is Z, this will automatically turn out to be Y. If you just do this. These three together define the ECI coordinate system or ECI frame. Okay? So P direction is the periaxis direction. For any orbit, this P direction is always constant, right? You know that by now. What is periaxis direction? What is periaxis? What is periaxis? Huh? Point of closest.
You said something. What did you just say? You said we know something.
Periaxis, you always know the periaxis direction. It's the point of closest approach, and if you just join the center of Earth to that point of closest approach, that will always be the periaxis direction. And if an orbit is given to you, if it's a Keplerian orbit, what does Keplerian orbit mean? You're not using it's. Go ahead, Quincy. Huh? No, I have not said anything. Go ahead.
I was going to say it's elliptical motion.
Huh?
I was going to say it's elliptical motion. You said Keplerian orbit. I was going to say it's elliptical.
Not necessarily. Keplerian orbit means the only force acting is gravitational force. See, when you use thrusters, then you're not in a Keplerian orbit, right? If you use thrusters, you'll obviously change your orbit, correct? So that's when you're not in a Keplerian orbit. If there is drag acting on your system, then you're not in a Keplerian orbit. Your orbit, any orbit, practically any orbit you talk about, will change, keeps changing. No, it's not that the orbit itself is changing. The orbiting body cannot sustain itself in any, even the moon, although it may take a lot of time to change, but it still changes. Even Earth's orbit is changing. Why? Earth's orbit is changing because Earth is experiencing other forces. Earth is not just under the influence of Sun. What is it under the influence of?
The whole galaxy.
Let's come on.
All R's and Venus.
What is closest?
Moon.
Earth is under the influence of Moon. Earth is under the influence of what else?
Venus.
Other planets. Earth, Mars, Venus. It's always under the influence of other planets. So it's Keplerian orbits only take into consideration the gravitational attraction of the central body. So it's also under the influence of solar drag. What is solar drag? Everything is under the influence of solar drag, right?
Is it like, could a solar flare create solar flare?
solar flare can increase the solar drag, but solar drag is essentially photons. What is solar radiation? Photons hitting. So if your photons hit you, light is also photons, right? So when photons hit you, it creates a drag. It's just like atmosphere hitting you, but it's on a much smaller scale.
Is that friction? Well,
it is kind of friction.
It's like friction between the magnetic field.
Magnetic field is another. Magnetic force is another force which causes. So Kepler did not think about magnetic force or solar pressure or atmospheric drag. If something is in a the International Space Station cannot sustain itself there by itself. It will not stay there if it did not have any thrusters, right? It would have spiraled in long time ago. So when we talk about Keplerian orbits, we talk about gravitational force only. And when we talk about that gravitational force only, if you put something in an orbit, it will always keep in that orbit. Okay? So that is Moon. Does Moon have an atmosphere?
No.
Moon does not have an atmosphere. So if we put something in Moon's orbit, the atmospheric drag is practically nil. So it will just keep on, even much lower orbit. So if you're racing just above the surface of Moon, if you just give yourself a push, you'll be doing that for a long time. You'll not come down. Even a foot or maybe a couple of feet away from the surface of the Moon. If you push yourself, you'll be orbiting like this. You'll never stop. Why does it not happen on Earth?
Because there's no gravity. There's not a gravity. Well, there's not atmospheric drag to pull you down and affect you.
On Earth, there is atmospheric drag to pull you down. It will slow you down and then pull you down. But for Moon, you'll just keep on doing that.
But then why didn't Neil Armstrong jump on the Moon and fall back down?
No, you cannot just fall. You have to. How do rockets get launched? You have to push. You have to give them a velocity, right?
Yes.
So if you give that velocity to yourself, so if this is your Moon, right? You'll not orbit if you just fall on it. You have to give that velocity. You have to just go above a little bit and then give that tangential velocity. Then you'll start doing this. Right? That's what orbit is. That's what happens here as well. You have to give that velocity. If you see a launch vehicle, it goes like this. And it just goes there. It does not just go there and release something. Then it will not go like this. It has to go like this.
So is Mars a little bit different? So
Mars has a different atmosphere, yes.
So
But
it's different than like the Moon and Earth together.
Mars is different. Every planet is different. Every planet has different atmosphere. Every planet has different magnetic fields. The gravitational force is something which is a function of. What is gravitational force a function of?
Of mass.
Huh?
Of mass. Function of
Radius.
radius.
Radius?
On Jupiter it rains.
Alright, so P direction is defined in terms of, defined in orbit plane. Okay? So this direction is clear to you? This direction, everybody? This is always, for a Keplerian orbit, this is always, it will remain the same. Okay, if you are orbiting, that's what your, one of your questions on the exam was, prove that angular momentum is conserved. What that means is, it's always going in this plane. It's orbiting. It doesn't change. For Keplerian orbit, it doesn't change. Okay? So this periapsis direction doesn't change. Once you identify that periapsis direction, the point of closest approach, you join the center and the periapsis point to change, remain the same. What is now, we define this W direction next. The W direction is what? It's simply angular momentum direction.
So that has nothing to do with the argument. That has nothing to do with that argument.
No, not this is W. This is not omega. Okay. This is angular momentum direction defined perpendicular to orbit. And Q again simply completes the right angle. Okay. So now what you see here is this is the P. Right? This is the periaxis direction. The center of Earth, and so what you see here is the green color is the orbiting plane, and this is the equatorial plane. You see this W here? You see a small h here? That means it is the angular momentum direction. Right? It has to be the angular momentum direction. Make sense? So now, when we talk about coordinate transformation, how do you go? When you're given these elements, how do you use it to figure out R and V? The coordinate transformation, this we talked about.
Is the R double dot, make R double dot equals U over R Q? Is that the equation?
No, the coordinate transformation I'm talking about is how do you go from the equatorial frame, how do you orient yourself from the equatorial frame into the orbital frame? So we talked about, remember, 3-1-3 rotation.
Yeah.
So this is my equatorial frame. Okay. So what I'm going to do is equatorial frame is this plane is the equator. The plane formed by my two hands. Right? So this is the x-axis, this is the y-axis, and this is my length is my height is the z-axis. Okay. So if I rotate, so you have 3-1-3. Just remember this. 3-1-3. About the three axis, I rotate by angle cap omega. Right? So this is about my height. I rotate. So this is z-axis, right? My height is z-axis. I rotate by cap omega. So you see cap omega rotation. You can actually see it here. This is your z-axis. Okay. This is x-axis and this is y-axis. So if I am standing, this would be x-axis and this would be y-axis. Okay. So if I am rotating about the z-axis, it will be by this angle, right? Cap omega angle, you see it? The rotation is in the equatorial frame. This rotation happens in the equatorial frame. It's about the z-axis. Then you have rotation about
The
x-axis. So you have this is the new x-axis, right? Now if you rotate it, if you do a right-handed rotation, that is the inclination. If you see what is the inclination, you see this angle, the angle between this plane and this plane is this. You see that is angle that is about this x-axis. Right? If you just attach, let's say you attach a plane to your this thing, let's say just a peg, you just rotate it in the right-handed side. You go from this plane to this plane. You don't see it? If you attach, if I have this right, if I attach my hand like this, okay, or
How did you, I'm stuck on the way you wrote that 3-1-3. Is the 3-1-3 that you just wrote up there, is that connected to this? Or is that,
so you have this is the This is my x-axis, okay? This plane is the orbit plane. If I do a rotation about this x-axis in the right-handed sense, you see that? This is the inclination we talk about. So this goes from the orbit plane to, the equatorial plane. This is the equatorial plane, right? It goes to equatorial plane to orbit plane. Huh? Because that is how the inclination is defined.
And where's the 3?
Huh?
The 3 on what you just said.
3 is done. 3 was the first one. So 3 was like this. So this is what my orbit plane. This is again orbit plane, okay? So I rotated about. This was my x-axis.
Let's see.
The z-axis, right?
Okay.
I rotated like this.
Okay.
The plane did not change,
Okay.
but this x-axis changed. X and y-axis changed. What is the new x-axis there? The line of nodes is the new x-axis.
And that's where you're.
The line of nodes.
The line of nodes is the new x-axis. This was the x-axis. I did this about z-axis. About z-axis means rotation 3, right?
Right. And then the line of nodes, that's
It aligned with the line of nodes. This x-axis aligned with line of nodes,
okay.
right? Did the plane change?
No.
So what do we do to change the plane? Now this is my one axis. Do you see one? One is x-axis, right? So I keep this, and what I do? It's about, so my new x-axis is not changing, right? My y-axis is changing, and this is z-axis. Z-axis is changing. You see it? Now this became the orbital plane. Okay? What is the final one? The final one is again 3, right? This is my new z-axis. If I do a rotation like this, that angle, if you see that angle is in the orbit plane. You see there, this angle is in the orbit plane, small omega. So you're actually changing that is the argument of periaxis. That's over there. You see how I went from equatorial ECI frame to 3, 1, 3. I'll try to show you. I actually, if anyone has those Lego sticks, I tried to look for them. I did not find any in Auburn. I actually went to visit all the Walmart and other stores. If you have them, bring them. I'll show you with those Lego sticks. You know what Lego sticks are?
You couldn't find those.
Connect.
Not Legos, the sticks.
Like connects.
People toys, I think. So if you have somebody has them lying around, or if you have nephews, nieces,
You're not looking for that. Like you could build a wall.
so you understand this thing, the going from, so how do we connect this? What is the math behind this? We have done the math behind this. So this is equal to what? R small omega R3.
Yes, C, what?
I'll do it. This is R P omega R 1 I R 3 F. So what is the way you should read it is the transformation matrix or the rotation matrix associated with transformation from Rajan from the rotation matrix from ECI to PQW, the rotation matrix associated with ECI to PQW transformation is equal to, so remember pre-multiplication, I told you pre-multiplication. The first rotation is this, rotation matrix, fundamental rotation about third axis biangle cap omega. Pre-multiply that by first axis, about first axis biangle inclination. Finally, rotation about 3 axis by argument of periapsis. You can, so this is a typical, this is a very 3-1-3 rotation. You can use any sequence. You can use 1, 2, 3. The angles will change. These angles, cap omega I and small omega, there is something common here you should notice. These define these are also the orbital elements, right? At the same time, the same orbital elements will take you from ECI frame to orbital frame.
So my question on the 3-1-3 was, so if this is the equatorial frame, you change the rotated about Z. You still inside the equatorial frame. And once you go into the overall frame, let's say you have to rotate about Y instead of Z again. So you have to rotate it about Y.
You can rotate it about. See, the thing is, you can go from equatorial frame to the orbital frame using any sequence 1, 2, 3, 3, 2, 1, 3, 1, 3, 2, 1, 2, 1, 3, 2, 3, 2, 1. But this has,
Does the name for the overall frame change, or whatever frame you're in at that time becomes the overall frame?
no, that is not the orbital frame. When you are in when you do the second rotation, you're still not in the orbital frame. You're in the orbital plane, but you're not in the orbital frame. You're not in the PQW frame yet.
Okay, and to get there, you have to rotate.
You have to still rotate in that plane. You did a rotation in that plane, right?
Okay, so this is
The first rotation you were in, before you did the first rotation, you were in equatorial frame. But once you did the rotation, you were no more in equatorial frame, or you were no more in ECI frame.
equatorial plane.
You're still in equatorial plane, but you're not in the ECI frame. The x-axis changed, right?
Oh, you're talking about
When we did the first one,
Oh.
the x-axis changed.
Yeah. Okay.
Although we were still in the equatorial plane, we were not in the ECI frame anymore.
Okay.
Because x-axis changed, y-axis changed, the z-axis was only remaining. So the same thing happens when you do the second rotation. We are in the orbital plane, but we are still not in the PQW frame or the perifocal frame. When we do the final rotation, we are aligned with the PQW frame.
Okay. So not the last.
Not till last you get into the frame, but the second will get into the plane.
Okay.
And one more time, you said that the multiplication order is from the large omega to the small omega.
Right, the rotation sequence is cap omega, I, small omega. This is 3, 1, 3. But the multiplication sequence is got it? So all you need to do is, so what is R 3 omega? This you know. This is simply 0, 0, 1, 0, 0, cos omega, sin omega, minus sin omega, cos omega. Right?
So if the multiplication sequence is just as it is up top, how does that relate to that other problem that I was talking to you about, where we had to do the y times x first? We couldn't do x, y. We had to switch the order.
Yeah. So if you do, let's say this is also achievable by some. So you have, this is 3-1-3 rotation, right? So if you talk about alpha, beta, gamma, okay, this would be what? Let's say 1, 2, 3. What would be the multiplication sequence? It would be gamma, beta, alpha. 3, 2, 1. And these, see these fundamental rotations, these are fundamental rotations. And we discussed fundamental rotations. Fundamental rotations are, so this is the fundamental rotation associated with 3. What is the fundamental rotation associated with 2? No? You don't remember? So fundamental rotation associated with 1 is what?
One is like in the center.
Huh?
One is
1 is not the center. So you have 1, 0, 0, 0. The first row, first column. Third row, third column. 3, 3. The third row, third, this is only 1. Rest is 0. You just populate cosine, sine, sine, cosine. This we have discussed in very much detail.
You're talking about the second axis.
Huh?
This is the first axis.
This is the first. So here it is relevant. The relevance here is 1.
Right. So I was thinking about
Second. So cos, cosine, I, sine, I, sine, I.
So what is the difference in this case with that small omega and the capital omega, because they both have the third axis?
But the third axis changes, right? It's not the same third axis.
Right. So like when representing this way, how in the matrix?
Its angle about, see, every rotation is, this is at that instance of time, right? Once you change, this is happening, see, you are dealing with 2D rotations, but you're actually experiencing a 3D rotation. You're going from one plane to another. So how do you go from one plane to another with a 2D rotation? Can you do a 2D rotation from one plane to another? You cannot do that. So what you're experiencing is 3D rotation. How do you go systematically from one plane to another? How do you calculate 3D rotation? This is how you do it. This is the mathematics. It doesn't matter at that instance. You have to. This applies to every 2D rotation. There are, how many 2D rotations are there here? There are 3 2D rotations, right? 3 2D rotations or 3 rotations. Simply every rotation you learn is just a 2D rotation. Do you know how to do 3D rotation? Do you know how to do 3-dimensional angles? I don't think you know how to do 3-dimensional angles.
I mean,
Oh,
you're saying like if we're like in the plane, like this being Z, Y, X, just whatever we did in the center, and then technically three-dimensional.
It's actually
the magnitude of each of the.
just focus on this. You can forget about 3D rotation. Just focus on this. You're doing a 3D rotation and using 2D rotations to go step by step. Okay? Just follow this. If you do this enough number of times, you'll understand what I'm saying.
So that multiplication will be a scalar multiplication after this.
No, it is a matrix multiplication. Why is it scalar?
No, after this, like once you do this matrix,
you'll end up with still a matrix. So what is the matrix? It's a 3 by 3, 3 by 3, 3 by 3. So what do you end up with? 3 by 3. A DCM is always 3 by 3. What is the other property of DCM? They are always, rows are orthogonal, columns are orthogonal. I told you that. What does orthogonal mean? You take the norm of this, you'll end up with 1. You take the norm of this, you'll end up with 1. You take the norm of this, you'll end up with 1. You take, norm is magnitude. Okay? You take the magnitude of row, first row, second row, third row, it's 1. First column, second column, third column, it's 1. You multiply and then take first column, second column, third column, you still end up with 1. This is also a DC. What is DCM?
Directional cosine.
Matrix.
Direction cosine matrix. Okay. Now coming back to this, we don't have much time. So now, let's just look at this. Okay. How do you calculate R? This actually itself, the calculation of R itself is actually very simple. Let's just finish that, and then so that you can attempt that particular problem which relates to R and B. Okay. See, your R is just give me like 5-10 minutes. We'll just so that you guys can attempt this problem. Okay? Yes, Helena.
What page is that on that side?
Huh?
What page is it?
Yeah, it's right on. So your R is h square over mu.
Helena was asking you something.
Yes, Helena.
I was on what page is that on in the book? What page is that on?
It's I think page somewhere around 216. 216. So R itself is h square over mu. The vector R is this. Okay. What do you know in this? Remember, you know A, E, I.
So we know H, E, and.
Do you know H?
If we
And
find,
they are constants.
I thought
If
you
you find,
you know H and you
Yeah,
know
you find
X
that.
the trigonometry.
You know A, E,
and the theta,
cap omega, I, and small omega and theta. Okay?
You don't know H.
You know H.
Well,
H is what?
H is.
Remember root of
No, I was just gonna wait
mu
it.
A
the square
1 minus E squared. You remember this from
from yesterday.
from yesterday? So that you know H, right? So what is this cosine theta and sine theta? Why is this cosine theta and sine theta? You remember? See this H, R is what? R is position vector, right? So if let's say this is a position. Okay, this is your focus. This is your R vector. This is theta. Because this component would be the x component, which is this is R cosine theta. This is the R sine theta component. There will never be a z component of either R or B. It is not possible. Okay,
Is that
because
supposed to be perfectly centered?
huh?
Is that supposed to be perfectly centered?
This one?
Yeah.
No, this is the focus.
It's elliptical.
It's elliptical. You see? It's
You said it's not going to be z component because it's from one point to another point.
No, Z, see R and B will always be in this plane. The Z is here, right? It will never, this is actually not the, this is not the XYZ, this is a PQW component. This is the P component. This is the Q component. There is no W component. Got it? There cannot never be a W component for R. Because R and P have to lie. See, if R has a W component, it means it will change the plane, which is not possible. Okay? So this makes sense. You can calculate R. Everything makes sense then?
Yeah.
So what is B?
B is
B is
H over R.
mu over H minus sin theta.
So what's the new part?
Huh?
What's the new part? Because we've been using that to calculate R.
No, you are not calculating R actually.
We're not calculating R?
You were given R, you are calculating these, right? Now you're given these and you're calculating R.
But I thought we did use that formula to calculate R.
You never use this. You're using this. But have you used this?
Okay.
The vector R.
Okay.
You have not used the vector R.
Okay.
So this gives you the vector R. See, these are X component, Y component, Z component.
So so it's gonna okay.
Okay, this itself is a vector.
Okay.
Okay. So you have E plus cosine.
So the three, the cosine, theta, the sine theta, and the zero.
Those are the different components.
Right. The way we're gonna incorporate that is how where the cosine theta isn't a problem.
Theta is given to you. That's what I'm trying to tell you.
So theta, it'll be the theta used from those three. I guess okay. So the R equation that we have up there. When are we gonna use the sine theta with that equation? Are we gonna use that in place of the cosine theta, or how are we gonna get those three different components?
You calculate, see it's a vector, right? This is the magnitude of that vector.
Okay.
This multiplied by the first
Okay.
row would be the X
component.
component.
Matrix with each
Yes,
component.
yeah, you can take it like this. This is just this.
Okay.
Okay, so
So this is how you express your vector, right?
That's kind of like a scalar product, scalar part of the whole matrix.
Right.
yeah, the
So
formula.
this is the scalar part.
And
This
then
is the
just
vector
put
part.
each of them and that would be.
Okay. So
Okay.
if I did not have this, I would have just erased that.
Mm-hmm.
But since I have this makes it a vector. But this vector is not in the ECI frame. That is what you have to remember. What this vector will give you is in the PQW frame. Okay. Now this is the vector in the B. And I'll just mention it here. Okay. Use this to calculate the B, vector B.
Okay.
Yeah.
And see, this is here. How did I get this? Can you tell me?
You
How
found
did I get this?
the derivative.
Huh? Exactly. So if I take a derivative of this, so what is the derivative of this itself? Is see here h or this is constant, right? I'll take a derivative of this plus the derivative. If you do the derivative, you'll understand what I'm trying to do. Okay. So see, it will be 1 over e square, 1 over 1 plus e square plus e into minus sine theta into minus sine theta. If you do that, you'll understand. Okay. Now the trick is how do you calculate? So this is you calculate PQW. There is one more thing you need to do. You need to really figure out R in ECI, right? That is our goal. Our goal is this. Our goal is not to calculate in PQW. you do this. C or R PQW is equal to C PQW ECI into R ECI. Okay. What you need is this. What you have is this. Can you calculate this? Because everything is known, right? So you just have to R, this implies R ECI is equal to C PQW ECI transpose, okay, into R PQW. If you were to calculate this, what would you do? You would take the inverse of this, right? And you pre-multiply both sides. This is a matrix. This is a 3 by 3 matrix. This is a column matrix. This is also a column matrix. If you wanted to find this, given this, what would you do? You would take the inverse of this matrix and you multiply both sides. Inverse into this matrix, what happens? Inverse into its matrix, what will you end up with? The inverse of A into A, you'll end up with the identity matrix. It's as if like multiplying this whole thing by 1. Inverse is nothing but 1. Or identity matrix is nothing but 1. Since it is a BCM, you don't need to take the inverse is equivalent to the transpose. So you just do this.
Because it's a DC.
And the final one is, again you do the same thing for B. B ECI is equal to C PQW ECI
Let's continue this one.
transpose B PQW. Please try to attempt this. It's a very simple this thing. You'll have a lot of fun. Use MATLAB for that. Don't do it with hand. It will become very. Thank you very much.
You said we don't, so we don't